In this segment, I'm going to talk about inertial versus viscous forces. This is a concept that is captured mathematically by Reynolds numbers, and Reynolds numbers in relation to body size. And this matters because as body size gets smaller, surface area increases relative to mass. What kinds of forces resist movements of animals? So here's some body shape, and it's moving forward. In order to move, it has to push the medium, which has mass, out of the way. So it has to push the water, which is mostly what we'll be talking about, but this also applies to air, out of the way. These are inertial forces because the water has inertia and the animal has to generate enough force to deal with the inertial forces. Now there's a second force that animals have to pay attention to, and that's viscous forces. Viscous forces occur because water forms hydrogen bonds with many of the molecules on the surface of an animal, and so the surface is viscous, it's sticky to the animal. And so as the animal moves, the entire surface is constantly encountering new water, which tends to stick, and it has to break that stickiness in order to move forward. So the combination of inertial forces and viscous forces determines how much energy it takes an animal to move. Now that changes with body size. Small animals have a high surface area to mass. You can calculate this or think through this for yourself if you think about a unit cube, one on a side, which has a surface area of 6 and a mass of 1 times 1 times 1 of 1. If we double it in each dimension, we wind up with a cube that is 2 by 2 by 2. And with this double cube, we now have 4 times 6 sides. 1, 2, 3, 4 times 6. Surface area is 24. And the mass is 2 times 2 times 2. Mass is 8. So we've gone from a surface area of 6 mass to 1, surface area ratio 6 to 1, in other words 6 times, to 24 to 8, which is 3. As animals get larger, they go from a high surface area relative to their mass to a lower surface area relative to their mass. In other words, a small animal has a high amount of viscous resistance relative to its mass, and a large animal has low viscous resistance relative to its mass. And that matters because as the animal is moving through the water, it has to push mass away and overcome viscous resistance. So how does that trade off and what's the effect on animals as body size changes? Well, a sphere minimizes the surface area relative to the mass. As an animal gets longer and longer for the same mass, the viscous resistance gets higher and higher. And as it gets narrower, if it's moving forward, it has less inertial force to deal with. So by getting longer and narrower, it takes less energy to move water out of the way. But by being longer and narrower, there's more viscous resistance because there's a greater surface area. So very small animals have a problem of very high viscous resistance, and very large animals have a problem of this large mass they have to push out of the way. So large animals tend to be fusiform or torpedo-shaped. That gives them a higher surface area to mass, but there's lower inertial forces required in order to push water out of the way. So let's think about animals of 3 different sizes. So imagine a bacterium. So a bacterium has very low inertial forces, low water to push out of the way, but it has high viscous resistance. So a bacteria moving through water is, if you scaled it to our size, it would be like you trying to swim through thick mud. And a bacterial flagellum is actually rigid. It's a rigid corkscrew, and it's like corkscrewing its way through mud or even corkscrewing its way through a cork on a bottle. As we get to somewhat larger animals, eukaryotes, which are have about 1,000 times the mass of a bacterium, instead of having a corkscrew type flagellum that just turns and turns and turns and corkscrews their way, they have a wavy movement of a flagellum that actually pushes water out of the way. But that flagellum is round in cross-section because as the flagellum moves, it has to keep pushing against the water, and being round in cross-section minimizes the viscous resistance of the flagellum. As we get to larger multi-celled animals, and this isn't nearly big enough compared to the bacterium, the cell here, fast-moving animals tend to be long and narrow because that minimizes the inertial forces to move water. And I'll get to this maximizes in a moment. And the viscous resistance, because their surface area is so small relative to their mass, the viscous resistance is not a major force. And the method that they use to move water, a broad flattened fin, it maximizes the push against water. It maximizes the inertia of the water that can be pushed behind. So as the water gets pushed back, the fish moves forward, pushing other water out of the way. And the viscous forces are not a serious problem for the fin because the major force is actually in pushing that large mass of water out of the way. So to go through this quickly again, 1, there are inertial forces, the mass of the medium that has to be moved. 2, there are viscous forces, the stickiness of the medium with the object. Those change with body size. Small objects or structures or animals have a relatively high surface area, in this case 6 to 1, compared to larger animals, which have a lower surface area, 3 to 1. 24 divided by 8 is 3, 3 to 1. The result of that is that for small animals, viscous resistance is the major problem for movement, whereas for larger animals, reducing inertial forces is the major problem. So small animals minimize viscous forces by being spherical, and large animals minimize inertial forces by being torpedo-shaped or fusiform. By being large and torpedo-shaped, that lowers the inertial force to push water away. So bacteria have corkscrew-shaped flagellae that spin. They don't wave, they're a rigid corkscrew, and they corkscrew through water, which minimizes the viscous resistance because they're fighting high viscous resistance, so they minimize viscous resistance. Eukaryotic cells are still often somewhat round in cross-section, at least oval in cross-section when they move, but the method they use, either cilia or flagellae, are round in cross-section. Again, because they're so small, they're minimizing viscous resistance. Whereas large animals are torpedo-shaped, and that large torpedo shape means you want to minimize inertial forces to move water. Their fins are flattened because that maximizes the push against water, moving water behind. That water moving behind propels the fish forward and forces water out of the way. So very small animals tend to be more spherical in cross-section and have to deal with the equivalent of swimming in mud or molasses, whereas for larger animals, viscous resistance is less and less of a problem. And so for animals like a blue whale, inertial forces far outweigh the effect of viscous forces, whereas for organisms like a bacterium, viscous forces far outweigh inertial forces.